Most people assume that the world we see is made up of tiny building blocks called atoms, and they themselves are made of smaller building blocks such as electrons, neutrons, and protons. And this is true. However, when visualizing these, we often think of them as matter. This, however, is not always true. Matter is just condensed energy, and the subatomic particles, atoms, photons, and even molecules that are so often thought of as particles are also waves, oscillations that carry energy. Light was the original problem. For centuries, scientists argued about whether light was a particle, a view held by Newton, or a wave, the viewpoint of scientists such as Huygens. But who was right?
Young's double-slit experiment shouldn't be too unfamiliar, and the equations behind it are not hard. However, it is often a difficult scenario to visualize. When monochromatic light is incident onto a surface of two slits, light diffracts and spreads out onto the other side of the surface. A screen placed beyond this surface will show constructive and deconstructive interference of light. This can only be explained if light was a wave. Even a single photon incident on the screen will diffract and interfere with itself.
So, that proved definitely that light is a wave then, no? Wrong! A proof of light being made of particles was discovered in 1887 by Heinrich Hertz. However, it was named after the scientist who explained the phenomenon. It is called Einstein's photoelectric effect. Light incident on a metal surface will liberate electrons from the surface, given that the light has enough energy to free the electrons and overcome the work function. But below certain frequencies, the energy of the light was not enough to liberate the electrons from the surface. Surely an electron could simply absorb more light to then gain enough energy. As it turns out, this is fundamentally wrong, as light travels in what is called a photon, a packet wave. An electron can only absorb one of these photons. Thus, if the energy is not sufficient to liberate the electron, then no photoelectrons will be produced.
After the contradicting results from the different experiments, along came de Broglie in 1924, suggesting if light acts as both matter and wave, then why not electrons? His suggestion brought up the idea that matter could act as a wave as well. After all, if matter is just condensed energy, as long as it moves, oscillates, it does the same thing as a wave. Therefore, the wave properties of matter should be determined by the mass, which is related to how much condensed energy there is, and its velocity. In other words, its momentum, lambda equals h over mv. He called these waves, matter waves. An example of matter exhibiting wave properties is an electron passing through a double slit with an opening similar to its de Broglie wavelength. Therefore, it diffracts and interferes with itself. Then why don't we observe matter acting like a wave in our daily lives? It is because for macroscopic objects such as ourselves, and the one we can see, the de Broglie wavelength is too small for any physical setup to measure. There are molecules that have small enough mass to have wavelengths that can be tested. For example, Buckminster fullerene. So what would happen if we threw Buckminster fullerene through a double slit? This fullerene has a special property. When it is thermally excited, it emits photons. So, theoretically, we would know which slit it goes through to interfere with itself, like the electron did in the Young double slit, right? Nope. When it is thermally excited and emitting photons, the fullerene acts fully like a particle, choosing a slit to go through. But in the case of not emitting photons, it still interferes with itself, much like the electron. So it is not a matter of being able to see it in daily life. We actually cannot observe it even in the microscopic world. This brings us to another quantum mechanics phenomenon, superposition. The most famous example includes a cat, but we are against animal abuse, so we will be avoiding that. In simple terms, superposition states that all possible states of anything all exist simultaneously. However, when an observation is made, the observed object is forced into one particular state. So when we are not observing, for example, the Buckminster fullerene, it exists in a superposition, where it is both a matter wave, as de Broglie called them, and a particle. The moment we observe it, however, it always collapses and chooses to be a particle. In simple terms, observation affects the results.
The uncertainty principle states that the complementary variables can only be measured to a certain degree of precision together. The most commonly known form of the uncertainty principle covers momentum and position with. Uncertainty in momentum times uncertainty in position is greater than or equal to reduced Planck constant over 2. But what does this have to do with the wave-particle duality? As the wave property of a matter depends on the momentum of the object, any uncertainty associated with momentum carries on to the wave property. This gives us the implication that matter and wave properties are also complementary pairs. This explains why we cannot both measure the full wave and particle properties of certain objects we would expect to exhibit both. However, we can measure some wave and some particle properties in experiments such as the double-slit experiment, where their properties are determined by the kind of measurement done.